This is the second lecture on DSP, where the topic of today is Introduction to Digital Signal Processing, continued from the last lecture, and we shall also discuss digital signals. In the last lecture, we talked about the course contents, the books that are recommended, Mitra and Oppenheim Scheffer for DTSP. We talked about a definition of a signal. A signal is a function of one or more variables. Signal is a function of one or more variables, and accordingly it can be a one-dimensional signal, two-dimensional signal, or multi-dimensional. And we also said that basically there are two kinds of signals, analog and digital. Analog can be continuous time CT or discrete time DT. A discrete time signal is not a digital signal. A discrete time signal is one in which the amplitude is a continuum. Amplitude is not discretized. On the other hand, the time is discretized. This signal is still analog only when a discrete time signal is passed through an A to D converter that it becomes a digital signal. Okay. So, there is a difference between analog digital, and in analog we can have two kinds of signals, continuous time and discrete time. And then we also emphasize the need for processing, why one should process a signal. This is to obtain a better quality signal than the original one. It could be, for example, noise filtering or improving the quality of a picture in terms of brightness or contrast or whatever it is. And we said that the signal processing that one can make again can be of three types. You can have analog signal processing or digital signal processing or mixed signal processing. And we also emphasize that analog signal processing dominated prior to 70s. Between 70 and let us say 2000, it is basically digital signal processing which got a dominance over analog, and the current trend is to have mixed signal processing, namely a combination of digital and analog. The next question that we talk about is, why digital signal processing? Why can't we do with analog signal processing only, because most of the signals in practice are analog. Now, DSP should be the natural choice if the signal is digital. For example, the rainfall data at Delhi over the last 20 years, on which is based the prediction for the next year. Predictions fail, sometimes they fail miserably as it has this year, but the data that you collect is a digital data. 1980 so many inches, 1981 so many inches. Now, the amplitude can be a continuum. So, it is a discrete time, but the amplitude or the number of inches of rainfall can also be coded if you so desire. If you want to do DSP, then the amplitude or the height of rainfall can also be coded. But you see the time is discretized 1980, 1981, 82. There is nothing between 80 and 81. There is nothing like a 1980.5 or 1980.41. So, the natural choice would be DSP, and this is what is done. This data is fed with many other parameters controlling monsoon or rainfall to a supercomputer, which basically does DSP. That is, what is DSP? Addition, multiplication and delay or recalling of past signals. Even if the signal is analog, one prefers to use DSP, and the reasons are many. DSP has many advantages over ASP or analog signal processing, and many a times it happens to be a less costly proposition. Digital ICs are available off the shelf at very low cost, and therefore, in many cases analog signal processing gives way to digital signal processing, even if the original signal is analog. How it is done is represented by this block diagram, where the input is analog, it is an analog input. Then we have a sample and hold device, which basically consists of a switch which samples the data, samples the analog signal, but it holds it for some time so that it can be converted to a digital form, because conversion from analog to digital requires time, and during that time the signal must be held constant. Then after the A to D you get a coded signal, that is most usual form is binary, which is then processed by a digital processor. What basically this does is combination of signals by multiplication, by addition and by recalling past signals, that is through delays. There are basically three operations: delays, multiplication and addition. So, this is what the digital processor does. It is a very simple device. It simply performs three operations. I repeat: addition, multiplication. Multiplication is repeated addition, only two signals at a time, and subtraction is also a form of addition with one of the signals negated or the sign bit is changed. So, in a sense there is no integration, there is no differentiation, there are no complicated operations which limits the usefulness of analog processing. And then the output of the digital processor is also a digital output, is also a sequence of numbers, and in order that this output be useful, you must convert back to an analog form. So, you have a D to A converter or a digital to analog converter. The output of the digital to analog converter is in the form of staircases, that is, there is a level of signal, to the next level it rises and then stays for some time, which is equivalent to the existence of high frequencies in the signal, because there are abrupt changes, fast changes at the staircases, and therefore, there are high frequencies present in the signal which have to be gotten rid of by an analog low pass filter, and the output, finally this analog output is the output that is to be useful. It could, for example, be a piece of music which has to be filtered from surrounding noise and perhaps mix up with other signals, and finally it has to be played, it has to be heard on a loudspeaker, and therefore you do require an analog output. Pictorially, this slide represents the basic operations. The first picture is that of an analog input which you wish to process by a digital processor, and this is what happens when you sample it. This is the analog input, then you sample at 0, at 2 microseconds, 4 microseconds, 6 microseconds, 8 microseconds, uniform sampling, and at each point 6 microsecond for example, you pick up the value of the signal at this point and then you hold it till the next sampling comes. This holding is required for A to D conversion, time is required, and the A to D conversion typically may look like a sequence of waveforms like this, where the positive output is 1 stands for positive and 0 stands for negative. There are many other choices of coding, but this is a typical coding where any signal, any pulse which is positive is taken as 1. For example, this is 1 0, okay, and then after processing by the DSP, which carries out operations of multiplication, addition and delay, maybe the output of the DSP is something like this, which now has to be converted to analog form. So, you have a D to A converter which again produces staircase waveforms like this, that is these codes are converted to amplitudes, volts or amperes, and a typical D to A output looks like this, which as I said is a contains high frequencies which have to be gotten rid of, and therefore you pass this through an analog low pass filter to get the desired output, which may typically look like this. Okay. So, this picture shows what exactly the operations which are involved in processing an analog signal by digital means. The advantages that accrue out of the use of DSP as compared to ASP or analog signal are many. First is the digital signal processor is less sensitive to component tolerances and environmental changes. In analog signal processing, change in any element, an inductance, a capacitance, or a small shift in the power supply causes a change in the performance. This also happens in digital circuits, but since you are coding a high amplitude by 1 and a low amplitude by 0, even if the amplitude changes by 10%, it does not matter, 1 remains 1, unless the amplitude drops down to the noise margin level, you have nothing to worry, and therefore DSP, digital circuits, are less sensitive to component tolerance and environmental changes. Then digital circuits allow volume production without the need for adjustment during construction or use. Even if the performance deviates a little bit, one does not worry, one goes on with volume production, and once the process is set, the timings and the steps, nothing has to be changed. Digital circuits are of course amenable to full integration. This is not possible for analog circuits because of inductance and transformer. A transformer cannot be made into an integrated chip. An inductance of a respectable value, if you want picohenries or so on, they are very small values, yes, they can be made, by ICs, but inductances of respectable values like a microhenry or a millihenry is very difficult to make, because inductance basically requires a large volume. Inductance is flux per unit current, and in order to generate flux you require space. You cannot generate a large amount of flux in a small space unless the magnetic permeability is astronomically high. Okay? It also depends on permeability. Very high permeability materials are not available, and therefore analog circuits are not amenable to full integration. Inductances and transformers have to be outside the chip. In digital signal processing, accuracy can be increased almost indefinitely by increasing the word length. Of course, the cost also rises. As you put more number of bits, you have to pay more, but the accuracy increases. In a in a analog signal processor, the dynamic range is limited by the power supply. You know, in an op amp, in an operational amplifier, the output cannot exceed plus VCC or minus VCC, it gets saturated. In digital signal processing, since we are handling numbers, there is no question of saturation. We can handle as large numbers as possible, and if fixed point if fixed point does not do the job, use floating point with characteristic and mantissa stored in separate registers, and you can handle very large dynamic range. This is not possible in analog signal processing, and the same processor can do multiple jobs. You can, for example, use the same processor to time share two different operations, and the following picture shows how this is done. The upper signal is one which exists only at 0 seconds, 2 microseconds, 4 microseconds, 6 microseconds, and so on. The space in between, you can put in another signal. This is time multiplexing. You can put in a signal at 1 microsecond, 3 microsecond, 5, and so on and so forth. All right. These two signals are then mixed up. They look like this. Okay. So, if there is a digital signal processing occurring at odd values of time, then it handles only the first signal. If the same processor also performs another operation during the even periods of time, I interchange the two. Even periods is the first one, odd periods is the second one. So, the same processor can perform operations on two different signals which have been time multiplexed, and then at the output you can separate the two. Okay. So, use of the same processor simultaneously for different operations is a great advantage of digital signal processor. The power is gone. The recording has to stop. Shall have to wait. What is the problem here?
No, our system they are working on UPS.
I see. So there is no problem in recording. Okay, wonderful. You give me a signal, Mr.
We can start right now, sir.
Okay. So Time multiplexing is one of the great advantages of DSP. You cannot do it with ASP if you mix two signals, because in analog signal processing it is a continuous time signal or discrete time, but if one mixes with the other, there is no way you can separate them. Continuing the advantages of DSP, a digital signal processor can be very easily adjusted for a different characteristic by simply changing some numbers, some coefficients. This can also be done in analog signal processing by varying a resistor or a capacitor or an inductor, but changing a number is much simpler than changing or varying an inductance, for example. It is a very elaborate procedure, changing an inductance. Varying a capacitance is not a problem, but then you have problems of contacts, you have problems of environmental changes and so on and so forth. Similarly, resistors, the potentiometer contact gradually wears off due to mechanical. There is nothing like this, you simply change a number, one of the coefficients, and then you get a different characteristic. In adaptive filters, in variable cutoff filters, this is required. One of the major and dominant advantages of DSP is that exact linear phase systems can be designed. This is not possible in analog signal processing. This has been a dream of communication engineers to get exact linear phase. Exact linear phase means there is no delay distortion. We shall come back to importance of linear phase in a later lecture, in more than one lectures, but this is one of the major advantages of DSP, that it can attain exact linear phase and therefore it permits processing without any delay distortion. One of the advantages of DSP is also that different parts of the signal processor can work at different rates. That is, the sampling rate can be different in different parts of the processor, and there are well established techniques for changing one sampling rate to another and vice versa. You can sample up or sample down without any problem. This facility is not possible in analog signal processing. When two amplifiers are cascaded, nominally the gain is the product of the two gains. However, this is not invariably the case in practice, because one amplifier loads the other. As soon as you put a loudspeaker at the output of your power amplifier, unless it is perfectly matched, the power amplifier output goes down. There is no such problem in cascading to digital circuits, provided you do not exceed the fan out of the circuit. So, there are no loading problems due to cascading. Digital signals can be easily stored in magnetic tapes and discs, including optical disc, for as long as one likes. No problem in storage, and very low frequency signal processing is possible with ease. At frequencies in analog signal processing, inductance poses a problem. There is no such problem in digital signal processing at very low frequencies. However, all is not roses with digital signal processing. There are disadvantages also, and the major disadvantage of course is increased complexity. You have to use more devices, sample and hold, A to D, D to A, low pass filter, then a low pass filter is required at the input also. So, it is increased complexity. Then the major disadvantage is that the frequency range for operation of a DSP is limited due to the limited rate at which you can sample and hold, sampling and hold devices, and also A to D conversion. This speed is limited. And in practice, ignore this data, in practice you cannot use a sampling frequency today with today's state of the art, which is more than 10 megahertz, and therefore if the sampling frequency is 10 megahertz, naturally signal processing cannot be done for more than 5 megahertz, okay, half of the sampling frequency. The other disadvantage is that if you have a purely passive circuit, inductance, resistance, capacitance, to do the signal processing, analog signal processing, there is no question of power dissipation. None of these elements dissipates power. However, is that correct? None of these elements dissipate power. The resistance dissipates. Resistance does dissipate, but it is much less as compared to the power drawn by digital circuits and dissipated in the active devices, the transistors. Okay. A typical AT&T DSP32C processor, which contains 405,000 transistors, dissipates 1 watt. There are no such problems with LC circuits. If you do not use resistors, LC circuits dissipationless, but even then one does use the DSPs because of their other dominant advantages. This picture is very rapidly changing. Power dissipation is one of the major challenges for DSP engineers, and one of the aims of TI, Texas Instruments, is to make digital circuits which will require no power supply, particularly for devices which are to be implanted in live bodies like the human body, the heart artificial transplant, or the ear, artificial hearing aids. Okay, they would not in future, if DSP engineers are successful, in future would not require a battery. Battery is the major problem. To make a small battery is a problem. If you want to put it inside the human body, it is a problem, and the longevity or the life of the battery. So, they are aiming at devices which will work from body temperature. As long as the person is alive and his body temperature is between two limits, the device will work. If the person is dead, then of course the device is useless. So, this is what it is, and one has gone up to several milliwatts. That is about it. It is still at the experimental stage. Now, about digital, we come back to digital signals. Well, a digital signal is obtained from an analog signal by sampling. So, what you get here is XA of NT. This is not a digital signal, it is an analog discrete time signal. It exists only at capital T, twice T, so on and so forth, but its amplitude can be continuum. Then you feed it to an A to D, and what you get at the output is a truly digital signal, which we indicate, which we give a symbol of X of n. The subscript A is lost because it has become digital, and capital T in the process is lost. Lost in the sense that when small n becomes a variable, small n can take integer values only, positive and negative, and each integer value in the corresponding discrete time signal corresponds to the integer multiplied by the sampling interval. So, capital T is lost in the digital signal, but if the signal was derived from an analog signal, then capital T has to be kept in mind. One way of interpreting x of n is that capital T has been normalized to 1 second. Capital T has been normalized to 1. However, it is a beauty of DSP and discrete time signal processing DTSP that the mathematical techniques for handling discrete time signals and digital signals are the same. There are difference equations, Z transforms, Fourier transforms and so on and so forth, they are the same. So, whether the dependent variable is a continuum like x n t or a discrete amplitude like x of n, the techniques are the same, and therefore, we shall use x n t and x of n interchangeably. We shall always take that the signal has been discretized in time as well as amplitude. And this capital T, the sampling interval, is obviously the reciprocal of the sampling frequency 1 by f subscript s. This is the symbol that we shall use for the sampling frequency, and as you shall see later, our signal processing must be limited to half of the sampling frequency. We can't go beyond that. Obviously, then digital signal is a sequence of numbers, and the sequence sometimes is simply represented as x of n, where n takes values theoretically from minus infinity to plus infinity, but at intervals of 1, minus 10,000, then minus 9,999 and so on and so forth. Or to show that it is a sequence, we sometimes give the symbol of x of n within within curly brackets. Okay. For example, we can have a signal like, let us say 0, minus 1, 1, 2, minus 2 and so on. I am writing it ordinary arithmetic, but I have taken them to be coded, that is quantized into integer numbers. In this is a sequence. In this sequence, how is n indicated? What is the value of n? N equal to 0 is indicated through an arrow, and one writes n equal to 0. Then it describes the complete signal. X of n equal to this, it means that n equal to plus 1 the value is 2, n equal to plus 2 the value is minus 2, n equal to minus 1 it is 0, n equal to minus 2 it is minus 1 and so on and so forth. So, this is a complete description and representation of the signal. We shall not write binary numbers here, we shall write the integer equivalent of the number. The sequence is not necessarily real, it can be complex. This is a real sequence, but we can have a sequence like 1 plus j, 2 minus j2 and so on and so forth. For example, if you want to derive an analytic signal as you know has a real part and an imaginary part, which simply means that these signals are orthogonal to each other. The imaginary part actually is also a real signal which is orthogonal to the real part, and therefore, the signal can be real or complex. The length of the sequence is the total number of samples in the sequence. If this goes to minus infinity and if this goes to plus infinity, then obviously it is an infinite signal, doubly infinite, it goes to the right and goes to the left also. But suppose we have a sequence 1, 2, 3, 4 with this as n equal to 0, then obviously it is a finite length sequence. The length of this sequence is equal to the number of samples in the sequence, that is the length of this signal is 4. Although small n is 0, 1, 2, 3, small n ends at 3, that is capital N minus 1, n equal to 0 to capital N minus 1 will make a length of capital N, because there is a sample at small n equal to 0. A sequence, if it exists from some value of n, let us say n equal to n1, and goes to the right up to any value that one likes, but on the left the sequence is all 0. N1 can be anything, N1 can be 0, minus 1, plus 10, whatever it is. Then the signal exists to the right only, and therefore it is called a right sided signal, right sided signal. On the other hand, if the signal exists only on the left side and is 0 on the right side, and so on, this is called a left sided signal. All right. A signal in general can be a combination of left sided and right sided. Okay. A signal can be a combination of left sided and right sided, provided it is what length? If it is finite length, then you can always view it as a right sided or left sided. If it is infinite length, then obviously it is a combination of right sided and left sided signals. A signal or a sequence can be even or odd, or a mixture of even and odd. Sequence can be even or odd or general. An even sequence is one whose left side is mirror image of the right side. For example, if you have, let us say, n equal to 0 here, then you have n equal to 1 and n equal to minus 1 is this, same amplitude. Then let us say n equal to 2, it goes like this, and n equal to minus 2, it goes like this, then it is an even signal. In other words, an even signal x e of n is the same as x e of minus n. X e of 1 is the same as x e of minus 1. The amplitudes are equal. This is called an even signal. On the other hand, an odd signal is one in which a signal is odd, x o n is defined as negative of x o of minus n. In other words, it is like this. We will ask you what n equal to 0 should be, but if n equal to 1 is this, then n equal to minus 1 should be this. It is a negative of that. Then n equal to plus 2, if it is like this, then n equal to minus 2, it would be like this. Okay. What should be the value at n equal to 0? 0, because x e of z, x o of 0 should be negative of x o of minus 0, which means that this must be 0. So, this is an odd signal. An even signal can have any value at n equal to 0. An odd signal must have a 0 value at n equal to 0. And in general, a signal is neither even nor odd, but it can be decomposed into two parts, an even part and an odd part, x o of n. Okay. In general, it is a combination of even and odd parts, and if you want to find out the even part, it is very easy, x e of n, you just put n equal to, you just replace n by minus n, then you get x of n plus x of minus n, you add the two, the odd part will cancel. So, it is x of n plus x of minus n by 2, and in a similar manner the odd signal, the odd part is given by x of n, subtract from this x of minus n and divide by 2, what you shall get is the odd part of the signal. And quite a few problems in the book on decomposition of signals into even and odd parts. Try to work out as many as you can. Then we say, then we introduce what is a periodic sequence or periodic digital signal. A signal x of n is said to be periodic if x of n is equal to x of n plus k n, where capital N is a positive integer, which means that x of n repeats after every capital N samples, all right. This is called a periodic signal, and smallest n, smallest capital N for the validity of this relation is called the period. Excuse me. The period therefore has no dimension, it is not in seconds or microseconds, it is a pure number, that is, it indicates the number of samples after which the sequence repeats. Why is it the smallest n? Suppose 20 is the period, then this repetition will occur for 40 also, for 60 and so on and so forth, but the repetition will not occur for 10, all right. So, the smallest value of n for which this relationship is valid is called the period of the periodic signal or sequence. We will show a little later that while a cosine omega t or a sine omega t is always periodic, this is not true about a cosine omega 0 n or a sine omega 0 n. We will show a little later that this is not the case. Then we define what is a bounded sequence. A sequence x of n such that the magnitude of x of n, whether x of n is real or complex, positive or negative, if the magnitude is bounded less than equal to some number capital M, which is less than infinity, bounded means less than infinity for all n, then x of n is said to be a bounded sequence. Then if the summation of magnitude x of n over its total length, in general from minus infinity to plus infinity, if this summation is bounded, if this summation is bounded less than equal to some number capital P which is less than infinity, then x of n is said to be an absolutely summable sequence, absolutely summable sequence. The definition clear? Then you can similarly define a square summable sequence, square summable. Square summable sequence is one in which the magnitude squared is summed up from n equal to minus infinity to plus infinity, and if this is less than or equal to some number q which is less than infinity, then it is called, x of n is called a square summable sequence. 1 by x, 1 by n, suppose you have a sequence 1 by n, is it absolutely summable? No, because 1 by 0 is infinity. Is it square summable? No, 1 by infinity is square, 1 by 0 squared is infinity squared, so it is not. So, this is called a square summable sequence, and you notice that this represents the energy of the sequence, okay, square of the amplitude, square of voltage with 1 ohm resistance is energy, square of current with 1 ohm resistance is also energy. So, in similarity with that, the energy of the sequence is defined as magnitude x n squared summed up over all the samples. So, a square summable sequence can also be called alternatively a finite energy sequence. Finite energy sequence. A sequence may or may not be square summable. Okay. Then we talk about, exactly as in analog signals, we talk about an average power. We have defined what is energy, and power is energy per unit time. Power is energy per unit time. In similarity with that, what we do is we find out the energy over a certain length, let us say n equal to minus capital K to plus K. Then this represents energy over the length. How much is the length? 2K plus 1. If I divide by the length 2K plus 1, then this will represent average power over the same length, right? Average power over the same length. Now, what we do is we allow capital K to go to infinity. We allow capital K to go to infinity. Then we have covered the total signal, the total length of the signal. So, this is defined as P average of the signal. Okay. So, it is a limiting process. You can't go on adding up infinite length sequences. So, what you do is you go to sufficiently large number, increment by 1, 2, 3 and so on, and see does the average power change. Usually sequences trail off at very large values of n, and therefore, this is a meaningful definition, the average power. If you have a periodic signal, then your job is very simple. A periodic signal of length of period n, capital N is the period, then all you have to do is you have to take the average over one period, because every period is identical replica of any other period, and therefore, what you do is you take x of n squared, sum up between, let us say n equal to 0 up to upper limit capital N minus 1, because at capital N it starts repeating, and you divide by capital N. So, this is the average power of a periodic signal. We have defined absolutely summable sequence, square summable sequence, which is the same as finite energy sequence, and then average power in a sequence. Now, look at some typical elementary signals, elementary digital signals. The most elementary signal is the delta n, and it is defined as 1 for n equal to 0, 0 n not equal to 0. In other words, its diagram shall be just one sample of amplitude 1 occurring at n equal to 0, and it is 0 on either side. This is the most elementary signal that one can think of. It is called a digital impulse. Now, if you compare with the analog impulse delta t is quite complicated as compared to delta n. How is delta t defined? It exists at t equal to 0 only, and the amplitude there is infinitely large. Now, infinitely large does not mean anything. You must define infinity, otherwise the function will be useless for us. So, delta t is defined as integral delta t dt from 0 minus to 0 plus, that is the area under the curve, is 1. This creates a lot of problems because it is not a function in the ordinary sense. It is an unlimited function, the amplitude cannot be defined. It can be defined only in terms of the area. However, there is no such problem in a digital signal. It is very simple. The amplitude is 1 at n equal to 0, it is 0 everywhere else. A combination of such impulse functions gives rise to a digital step u of n, and u of n is a signal which is 1 for n greater than equal to 0, u of n is equal to 1 for n greater than equal to 0 and 0 otherwise. Obviously, u of n can be written in terms of delta n. It is summation delta n minus k, k going from 0 to infinity. Put k equal to 0, this delta n describes this, delta n minus 1 describes this, one sample delayed, delta n minus 2 is this. So, u of n is very simply related to delta n minus k, delta n. Delta n can also be related to u of n. Delta n is simply one signal of amplitude 1 occurring at n equal to 0. Now, all the rest are 0. Obviously, delta n can be written as u of n, from which you subtract from u of n, you subtract all that occurs to the right of this, which is simply u of n minus 1. Therefore, delta n can be written as u n minus u n minus 1. There is a mistake in the textbook, please note that mistake. I think our time has come to an end, and therefore we will stop today here.